Welcome to the training session on mountain waves and orographic enhancement. My name is Dan Bikus. Ed Zoke assisted me in putting this together. Our learning objective is to how to make optimal use of capabilities of the GOES-R series in identification of mountain wave clouds, which may also be referred to as orographic cirrus or Lee wave clouds. We'll address the benefits of greater spatial resolution and discuss the appropriate bands and products for identification. The mountain wave clouds or orographic cirrus that we'll be discussing are stationary cirrus that develop to the lee of a mountain range. Under the condition that a stable layer exists from the mountain ridge to the upper part of the troposphere, and wind direction is nearly constant, a wave is produced by the mountain ridge and is transmitted to upper levels. If sufficient moisture exists at upper levels, these orographic cirrus or mountain wave clouds will develop. These are important to account for in your forecast because they can play a significant role in temperature. GOES-16 imagery from the 10.3 micron band for 22 November 2017 shows multiple regions of cold cloud tops. However, for mountain wave cloud identification, we're interested in the clouds that develop along the ridge tops and exist only in the downwind direction. In other words, these type of clouds are quasi-stationary and they're tied in to terrain features, while other clouds advect along with the mean flow. During the loop, we notice the expansion of very cold cloud tops in western Montana, extending southward to Wyoming, implying that the mountain wave clouds are becoming thicker. The 10.3 micron band should be the primary band for analyzing mountain wave clouds since it highlights the typically very cold cloud tops that are locked into terrain features. Later, we'll discuss other bands and products that can be useful as well. Is there any other useful information from the various bands available on the GOES-R series? Well, the water vapor bands do provide value as well. In this four-panel, we have the 10.3 micron band along with the GOES-16 3 water vapor channels. One of the signatures you may observe in the water vapor channels is a region of warmer brightness temperatures associated with subsidence on the upstream side of where mountain wave clouds develop. At times, these may be a precursor to mountain wave cloud development. Of the 3 water vapor channels, which channel depicts the upstream subsidence signature the best, and why? I'll go ahead and highlight the upstream subsidence signature just west of the mountain wave cloud of interest in western Montana. Note that the subsidence signature shows up very well in the lower water vapor band at 7.3 microns. The signature is much more subtle over here in the mid water vapor band at 6.9 microns, and the signature is virtually absent in the upper water vapor band at 6.2 microns. The physical reasoning is due to the weighting function profile as discussed in the water vapor band's SatFC-G module. The 7.3 micron band weighting function profile sees the lowest altitude layer of the 3 water vapor bands. Typically, the strongest substance is associated with the stable layer that develops just above ridgetop level. Therefore, the 7.3 micron band is best suited to see that layer relative to the other 2 water vapor bands. However, for some events you may see a subsidence signal in all 3 bands, but the 7.3 micron band will likely still show the strongest signal. As you develop experience in looking at mountain wave clouds near CWA, you may notice trends in the subsidence signature with the 3 water vapor bands that could prove useful in forecasting mountain wave clouds. Finally, note the region of clouds and moisture approaching from the west and advecting towards the mountain wave clouds of interest. The wave clouds grow rapidly soon after the arrival of this feature. There are other bands and products that can provide additional information on mountain wave clouds. During the nighttime hours, the 10.3 and 3.9 micron bands have similar brightness temperatures. During the daytime hours, shortly after 14 UTC in this loop, note the brightness temperatures at 3.9 microns become considerably warmer compared to the 10.3 micron mountain wave cloud region. That's due to the introduction of the reflected solar component at 3.9 microns. This is particularly true over the mountain wave clouds of interest in western Montana, where brightness temperatures warmed from about -70 Celsius to slightly above freezing. The other higher clouds that are advecting along warmed only to about -20 Celsius. Research has shown that smaller ice particle sizes reflect more solar energy than larger ice particle sizes. Thus, the existence of relatively small ice particles in the mountain wave clouds can explain the warmer brightness temperatures at 3.9 microns compared to all the other ice clouds. Finally, note the nighttime microphysics RGB in the bottom, which can also tell you something about cloud particle size. However, for this case, during the nighttime hours, we can see this green speckling over the mountain wave clouds in western Montana, which implies supercooled liquid water. But we know from the 10.3 micron imagery, cloud top temperatures are around -70, well below the homogeneous freezing temperature. So why do we see this false signature? There's two possible explanations for this false signature. First, temperatures at 3.9 microns are cold enough to allow noise to appear in the imagery, and the 3.9 micron band is contained in the green component of the nighttime microphysics RGB. Secondly, the existence of relatively small ice particles. When very cold clouds exist at night, use 10.3 microns rather than 3.9 micron imagery or a product that uses the 3.9 micron band, such as this RGB, due to significant noise in the 3.9 micron band. We move on to a different case. This is in April of 2018, and we're focused over Colorado. Arguably the best way to look for mountain wave clouds is a 4-panel display with highest priority on the IR band at 10.3 microns. The development of mountain wave clouds shows up best in the 10.3 micron band, since it shows very cold cloud tops that are quasi-stationary, since they're locked into the terrain and advect downstream. Note that there's considerable high cloud cover advecting through the region of interest, mixing in with the mountain wave clouds, which can make it difficult to identify the mountain wave clouds. Next, we look at various channel difference and baseline products to help discern mountain wave clouds from the high-level clouds that are moving through. In the upper left, we have the cloud particle size distribution baseline product. Recall that mountain wave clouds are characterized by relatively smaller ice particles. This product isolates the smaller ice particles, which are color enhanced as purples and blues that originate along the front range and appear locked in to the terrain. Similarly, the day fog channel difference 3.9 minus 10.3 micron product can be useful during the day. This difference product subtracts out the emitted component so that we're left with the solar reflected component. The large positive values over the mountain wave clouds, indicated in yellows and reds with this color table, indicate relatively small ice particles. Remember to use these channel difference and baseline products in conjunction with the 10.3 micron product to note where the colder cloud tops exist. In summary, when using GO 16 or 17 to identify mountain wave clouds, right at the top of your list should be the 10.3 micron band. You're going to look for quasi-stationary clouds that are locked to the mountains and advect only in the downstream direction. Since these clouds are relatively thick, they tend to be quite cold at 10.3 microns, and visually may appear thicker in the visible band as well. They tend to be colder at 3.9 microns than 10.3 microns during the daytime. Therefore, the channel difference will be positive. You can make use of the channel difference product or certain baseline and RGB products that can highlight smaller ice crystals being more reflective. Finally, water vapor bands can show an upstream subsidence signature and also indicate regions of upstream moisture that may modify the wave clouds.